Need TV. December 1st, we're talking about Pluto tonight. We will be talking about the asteroid belt series and Vesta with the Dawn mission. Lucy McFadden from Goddard Space Flight Center. Hal is going to be great tonight. Lucy's going to be fantastic in December. I pity the person who has to sandwich between them, but well, I will get you somebody. All right, we got our group. Is this our group from Cross Keys? Yes. Yes. All right. This is a group from Cross Keys Village in New Oxford, Pennsylvania. I was actually just up there a few weeks ago giving a talk, and they brought a big group. So everybody move in, squish over. They brought a big group because they knew Hal. I advertised you really well, Hal, okay? So you're going to have to deliver tonight. And January, as we start 2016, I haven't actually done my 2016 scoping yet. So they will be posted when I do have them on our website. We have our Go link, hubblesite.org, Go Talks. You can also just go to your favorite search engine and type Hubble Public Lecture. You should get this page, and we have our list of our speakers. We also, for those of you who have not been here before, since I see we've got a bunch of people, how many people haven't been here before? Okay, all right, that's about a third of the audience, okay? We've been recording these and webcasting them since 2005. That's 10 years of these public lectures recorded in our webcast archive. This is a link to our webcast archive right down here on this page. So you're going to see a great talk tonight. There are a lot of great talks in the archive that you can go back and take a look at. All right. If you would like to know about the speakers, the mystery speaker for next month, and so on, sign up for the announcements. We have, for those who've been here previously, a relatively new way of signing up. You go to mail list, that's a double L there, .stsci.edu. You click on Public Lecture Announce and give your email address, and you will not be getting any spam. If that's too complicated for you, you can just write your email address down on a piece of paper and hand it to me at the end of the lecture, and I can go to maillist.stsci.edu and add you to the mailing list, okay? If you would like to send us comments or questions, you can send them to publiclecture@stsci.edu, or if you want to just send an email to that and say, sign me up for the mailing list, we'll have your email on that from your message, okay? If you want to follow us on social media, Hubble is on Facebook and 2 different Twitters, and on Google Plus, and on Pinterest, and maybe a few more that I don't know about. Myself, I do a blog on Hubble site called Hubble's Universe Unfiltered, and I'm also on Facebook and Google Plus and on Twitter, though not as often as I would like, because it takes a lot of time to do social media. I got other things to do as well. All right, for those of you who like that. Weather permitting, I'm told it is not permitting tonight. I got an email just before 7 o'clock tonight saying, the clouds are not going to part for us, so there will not be observed across the street. Keep coming to the public lectures, and a few months out of the year, we'll definitely be able to let you go across the street and do the observing at the Maryland Space Grant Observatory. But you don't have to do it just during public lecture. You can also come every Friday night if you go to md.spacegrant.org. They will have their listing of their nights when they open the telescope. I believe it's most every Friday night. Okay? All right. Now, our news from the universe for October 2015. Our first story tonight, the care and feeding of quasars. So, first of all, what is a quasar? Well, this is a quasar. All right, this is a quasar MC 1635 plus 119, which emphasizes the fact that in astronomy, most things don't have beautiful names like, the Dumbbell Nebula or the Andromeda Galaxy. Most of them just have catalog numbers, okay? And this is QSO MC 1635 plus 119, which is about as catalog-y as you can get. But what makes it interesting is, you see those spikes on it? Those are diffraction spikes. That looks like a star, but it's not a star, okay? It's a quasi-stellar object. That's where quasar comes from, quasi-stellar object. It's something that looks like a star, but isn't a star. It's actually in a very distant galaxy. And if it's bright enough to look like a star, but it's actually in a very distant galaxy, it's got to be really, really powerful. So from the ground, we were basically able to see these quasi-stellar objects, these quasars, and we're trying to figure out, all right, where are they? What types of galaxies are they in? And it was one of the things that Hubble did back in the 1990s. This was a press release from 1996, where we saw these quasi-stellar objects, and with Hubble's resolution for some relatively nearby quasars, we were actually able to see the host galaxies around these quasars. We were able to look in and actually see that these galaxies, these quasars truly were within galaxies, able to see the galaxy. Because generally the quasars are so bright you can't really see the galaxy around it. With Hubble's resolution, we were able to do this back in the 1990s. But we wanted to know more. And a recent survey looked at 11 very, very bright quasars. But they were actually dimmed because they were dust enshrouded. The galaxies have lots of dust in them, so that the brightness of the quasar is actually dimmed a lot. So these are actually infrared observations of 5 of the 11 quasars that they studied. So here again, you can see that it's got the diffraction spike, so these look like stars, but they're actually very powerful sources. These are powered by supermassive black holes at the cores of galaxies. So we know they're in the center of galaxies. What we want to understand is, what is the galactic environment like? Well, in that intermediate time, besides Hubble getting extra resolution, extra capability at infrared, we also developed computational techniques where we're able to very supremely subtract off the light of the stars, or subtract off the light of the quasars. So this is what it looks like with the quasar on. If we go in and use our sophisticated point spread function matching, we can subtract off the light of those quasars and then see the galaxies around it. And the result of this study was that some of the most luminous quasars, and these are quasars that are in galaxies that are about 10 to 12 billion light years away, some of the most luminous quasars are in galaxies that are interacting and merging. That the interactions and the mergers appear to be feeding the supermassive black holes, and that's what's powering these very luminous quasars. So, luminous quasars are a lot like that plant in Little Shop of Horrors, because you have the collision and you feed the supermassive black hole, you feed the monster at the center of the galaxy. Our second story today is unveiling a visualization. So we're going to talk about the Veil Nebula. Now, the Veil Nebula is a huge nebula across the sky. Matter of fact, we usually talk about it in several different parts. Well, when I look at this one, I actually think of it as sort of the question mark nebula, because it looks like a question mark there. All right, the Veil Nebula is a supernova remnant, okay? It is the result of an explosion of a star that blew its guts across interstellar space, and you can see the bubble formed, all right, when that star exploded. And we have what's here is the eastern part of the Veil Nebula. And for those of you who aren't astronomers, when you look up at the night sky, north is up and east is to the left. I know when you look at a map, east is to the right, but for astronomers looking up at the night sky, east is to the left, okay? So this is the eastern part of the Veil Nebula. This is before somebody goes, Mr. Summers, you're getting that wrong. No, okay? I'm intentionally backwards, okay? And then we've got this region along in here, which is called Pickering's Triangle, if I remember correctly. And then we have the western part of the Veil Nebula. And what we're going to look in is at this western part, this region right here. And this region is often called the witch's broom. As you can see, it sort of looks like a witch's broom. Although I've been staring at this so much for the last month, I'm starting to see a peacock. Does anybody else see that? Okay, you can see the peacock tail here, not with them fanned out, but with them down, okay? You can sort of see a peacock here. All right, well, this is what happens when you stare at the same image for a month while you're making a viz. Okay, but this is called the witch's broom. And up here in the handle of the broom, okay, is where Hubble took a brand new image. Now, as you know, Hubble has done several new images for its 25th anniversary. We started out with the pillars in the Eagle Nebula in January, and we did those great visible and IR composites of those. And then in April, we did the star cluster Westerlund 2, which you may remember. Well, this month, or last month, I guess, we did the Veil Nebula, a tiny piece of the Veil Nebula, and this is Hubble's image of it. Now, it's extremely colorful, right? However, of course, this is not what the human eye would see. These are specific wavelengths that Hubble has looked at in order to see the different elements in the nebula. All right. So if I remember correctly, oh wow, I forgot. I'm losing it. The blue, I believe, is oxygen. The red is sulfur. No, and the green is, or red or green is sulfur, and red is hydrogen in there as well. And I think there might be some nitrogen. Oh, I should have. I had this all in my head 2 weeks ago. Anyways, so you're seeing the various colors indicating the different elements in the nebula. Okay. So when we get these cool images, they of course come to our team and say, hey, can we have this in 3D? Can you do a visualization of it? And we look at it and go, okay, let's see what we can do with this. All right, well, first thing we do is we actually start with a slightly larger image. If you look over here on the side, you can see it's got a ratty edge over here because we're going to start with a full field image we crop down when we do our press releases, okay? And then the next thing we're going to do is we're going to say, all right, all those stars are distracting from the nebula, so poof, there we go, we get rid of the stars. All right? It's just like that. It's just this one little button on our image processing. Poof, there go the stars. And if you believe that, okay. So then we got to figure out what are we going to do, because remember, this is part of a giant bubble. All right? And to me, actually, the cool story is this giant bubble, but we couldn't really model the entire bubble. So what we've got here is just a thin little piece, which is a shell along the edge of a bubble. And, all right, and we recognize, all right, there are some ripples into it, okay? And if you can see, sort of, there's a ridge along here, and then a ridge along here that's sort of like a bunch of ripples on a landscape. So we're going to try and model this so you can start to feel the ripples in this bubble, okay? So we want to take each of those colors, separate them out. We want to do the individual elements separately. So here is the blue of it. We extracted out the blue. And then we extracted out the red and the green, but the red and the green look very much alike. So we wrote some code to take the red and the green and match them where they're equal and turn that into a yellow channel. Okay, so here is a yellow channel of where the red and the green are equal. And then there was the excess, oh, sorry, wrong button. The excess red that goes over and above what's in the yellow channel, and the excess green is actually in here, but there's almost very little of it. And then we could get the emission from the different elements and place them at slightly different places in 3D. All right, so here is our 3D model of this nebula. And you can see it's got these ridges, and there's all sorts of tiny little structure in there that our modelers were able to put in. And what I thought was going to happen with this was that we're taking a flat image and then we're stretching it into the distance, and all those pixels are just going to spread off into the distance, and the whole image is going to get stretched out, and it's not going to look good. It didn't. Actually, when we popped the image onto it, it still felt really good. So we're able to take the image and put it onto that wave in 3D. Then, of course, we need to take the background stuff in the nebula, because there's a little bit of other stuff, push that on a layer behind that. We need to have in the background stars, the stars that we get erased, we bring them back in, some of them in the background, and a bunch of them in the foreground, okay? And then we pull that all into our 3D model, where here is that wave of the nebula here. This is the background part of the nebula. Here are 5 versions of the background stars, because the camera's going to swoop all over, and we need to make sure that you see stars in the background of all of them. And then we've just got a few stars in the foreground. Now, normally when we float into this, we want to have lots of stars in the foreground to give you that 3D feel. In this case, we actually had to get them off screen because the camera is going to take a sort of a roller coaster type motion, and having the stars in there is actually a problem. So here it is with flat shaded, and finally put together, we have that 3-dimensional nebula. So this looks kind of hokey, doesn't it, right? You look at the 3D model and you go, how is that ever going to be an enjoyable thing? But you know what? When you put it all together, it actually does work. So this is our trip. Whoops, that's not what I wanted to do. Come on, push play. All right, how about no? All right, I don't know. It's got this thing on my screen that won't let me. There we go. All right, so we get those stars past you, get those flying off. And then we swoop up to show you the nebula and then come down to come rising up over those ripples in the nebula. And you'll notice that the emission, the colors of the nebula are at slightly separate layers, so you can see that the emission from the different elements is coming from slightly separate layers inside the nebula. So since this is going into the broom handle part, we nicknamed this "Flying Off the Handle" in the Veil Nebula.
Where was the original star that created the nebula?
It would be toward the center of that giant bubble. I do not believe, since it's a supernova explosion, it generally leaves behind either a neutron star or a black hole, and I'm not sure if anyone has ever successfully identified what would be the stellar remnant from the supernova explosion. Okay. All right, our featured speaker tonight is Hal Weaver of the Johns Hopkins Applied Physics Laboratory. You're getting all excited, you're ready to applaud yet. Well, I have to actually tell you his amazing pedigree before you can applaud, okay? All right, so he got his degrees from Duke University for undergraduate and the Johns Hopkins University for his master's and PhD. In doing his PhD, he analyzed spectra of comets from the International Ultraviolet Explorer. He also went on to do infrared observations of Comet Halley using the Kuiper Airborne Observatory. I was actually very impressed with the number of different instruments and missions you've been working on. He worked with the Far Ultraviolet Spectroscopic Explorer, also called FUSE. He's worked with the Hubble Space Telescope, and he was the chair of the science team investigating Comet Shoemaker-Levy 9 when it hit Jupiter back in 1994. He also worked on the ESA-led Rosetta mission as the co-investigator on the ultraviolet spectrograph, and he joined the Johns Hopkins APL in 2002. He is currently the project scientist of the New Horizons mission, and he, along with the gentleman sitting to his right, worked on the discovery of the 4 new moons of Pluto, with the Hubble Space Telescope in advance of New Horizons getting to Pluto, so that we take the 2 targets for New Horizons and multiply it to 6 targets. So the cooperation between one NASA mission and another made a fantastic payoff last July, which he will tell you about, okay? And just one other side note, in 1996, asteroid 1984 FN was renamed officially Asteroid Hal Weaver. So, ladies and gentlemen, a man with an asteroid named after him and a lot of Pluto in front of him, Hal Weaver.
Okay, everybody can hear me? Yes. Thanks a lot for coming out tonight. It's pretty late in the evening, but the secret to getting a big crowd, Frank, is to stop the rain. That's what I did, first of all. But no, it's Pluto. Everybody loves Pluto, right? And after a long 9.5-year journey, the New Horizons spacecraft on July the 14th, just a couple of months ago, flew just 7,800 miles above the surface of Pluto. And the results that we've gotten from that have just been really breathtaking for the science team. And it's a mission of delayed gratification is what I like to say. You know, we took off a long time ago and finally reached it, and it was worth the wait. Let me just, first of all, say that usually we just skip over the first slide, but in this particular case, I just wanted to point out that over here is an artist's rendition of the New Horizons spacecraft as he perceived it to be coming in to visit Pluto and Charon, right down here. And this is a real image taken from the New Horizons spacecraft as we approached. One of the iconic views, now iconic views of Pluto and Charon in natural color. We'll see a lot more of this in a few minutes. And then down in the lower left, look at this, just incredible. After we flew by Pluto and looking back at the sun, and I'll say a lot more about this in a few minutes. So, we're on our way to talk about the New Horizons mission. Let me just, before I get into the results, I just want to say a little bit in way of background so you'll understand the context of the mission. This is the initial reconnaissance of what we call the solar system's third zone. Now, what do I mean by that? If you think about the architecture of the solar system, we divide it into 3 regions. You have the terrestrial planet region, which is comprised of relatively small rocky planets, Mercury, Venus, Earth, and Mars. And then you go out into the second zone. You step a little bit farther out and you get into the region of the giant planets. Huge monster planets. Jupiter's 320 times as massive as the Earth, has this giant gaseous envelope around it. And then you go out to Saturn, Neptune, Uranus, and Neptune. In this little cartoon view of the solar system, our region, the terrestrial planet region, doesn't even rate. This is a big picture view of our solar system. But after you step beyond the giant planet region, you get into what we're now calling the third zone that we didn't even know existed until the 1990s, called the Kuiper Belt. And it's represented here in this cartoon fashion by these white dots. It's sort of a donut-shaped region surrounding the sun. Roughly, most of the objects are roughly in the same plane as all of the other planets. That's what we call the ecliptic plane. But they also go all over the place as well. Pluto's orbit is shown in yellow here. Okay, it's actually tilted by 19 degrees to that plane of the other planets, and it's also not circular, unlike the Earth's orbit, which is almost perfectly circular around the sun. Pluto actually travels inside of Neptune's orbit to about 29 astronomical units from the sun. You know, the convenient yardstick to use for the solar system dimensions is 1 AU. The average distance between the Earth and the sun is called 1 AU, 1 astronomical unit. Pluto right now is about 32 AU away from the sun. But it actually came within 29 AU inside of Neptune's orbit in 1989, and it's on its way out now, and it'll go all the way out to 48 AU. It's an elliptical orbit, very different from the other objects in the solar system. So the New Horizons mission is the first in situ reconnaissance of this newly discovered region in the solar system. This is the frontier of our solar system and the frontier of planetary science. And it turns out that this region is more populated than anywhere else in the inner solar system. Okay, most of the objects in the solar system are in this Kuiper Belt region, and we want to see what they're like. They also tell us, because they're so far away from the sun, they've been kept cold most of the time since the time they formed 4.6 billion years ago. They've preserved better than almost anywhere else in the solar system what the conditions were like at the time of the formation of the solar system. And the discovery of the Kuiper Belt And the three different classes of objects in the Kuiper Belt, turns out there are three families of objects in the Kuiper Belt, really completely revolutionized our view of the solar system's formation and evolution. Most of us were taught that all of the planets, their current configurations, they've been there in that configuration forever. But it turns out that with the discovery of the Kuiper Belt and the recognition of these different families of Kuiper Belt objects, that we now realize that the solar system, the early solar system, went through this tumultuous period when there was a huge amount of what we call radial migration. The giant planets, Jupiter, actually came almost within Mars's orbit and then went back out again. And all of the other giant planets just came in and then back out. Uranus and Neptune, we think, actually switched places. This was all happening within the first few 100 million years of the solar system's existence. And all of that knowledge, the understanding of what was happening in the early solar system, was motivated by the discovery of the Kuiper Belt and our understanding of the different objects in the Kuiper Belt. But it is way the heck out there. You know, more than 30 times farther away from the sun than the Earth is. And it takes a lot of energy to send a spacecraft to the Kuiper Belt. So in the case of the New Horizons mission, we had to get the biggest and baddest rocket that was available, the Atlas 551. This is a picture of the rocket, 200 feet high. Our spacecraft is like a little hood ornament on the top of this giant, oops, let me go back, sorry about that. So 200 feet from this end to this end, 5 solid rocket boosters surrounding the core engine here, a Centaur second stage, and then even a third stage, this Boeing Star 48 third stage. Several million pounds of thrust to propel a 1,000-pound spacecraft out to Pluto. That was what was required, okay? And that's what we did. And I always like to show this. It takes me back January the 19th, 2006. 2 p.m. in the afternoon. The fastest spacecraft ever to leave the Earth. And still it takes 9.5 years to get to Pluto, but it was leaving the Earth so fast, more than 30,000 miles per hour, it passed the orbit of the moon in only 9 hours. So we took off at 2 p.m. I went out on our porch at 11 p.m., looked at the moon. It was a full moon. The New Horizons spacecraft had already passed the orbit of the moon. It took the Apollo astronauts 3 days. Okay? We actually passed by Jupiter in only 13 months, also a record. It took the Galileo spacecraft, the spacecraft that was dedicated to the study of Jupiter, 5 years to get there. Now, this is the, just a color-coded view of the path of the New Horizons spacecraft as it left the Earth. The Earth is down here, and color-coded by year, starting off with black and then purple and blue and so forth. Each year you can see where the spacecraft was as it's heading out, and you can see the relative configurations of all of the other objects in the solar system. Okay, so like I said, in late February of 2007 is when we passed Jupiter. Now, we actually directed the spacecraft near Jupiter in order to pick up a gravity assist from the incredible, Jupiter is so massive, like I said, 320 times as massive as the Earth. Well, we stole a little momentum from Jupiter as we passed by and increased our speed by 20% and cut more than 3 years off the travel time to Pluto. That was the primary purpose of flying near Jupiter. But in fact, we flew close enough that we got fantastic science as well. I don't have time to go into that, but we saw the most detailed view of the volcanoes on Io were mapped by the New Horizons mission. But anyway, as we stepped out, so in 2008, we passed by the orbit of Saturn. 2011, Uranus. Finally, in 2014, just a year before the flyby, we passed by Neptune. And finally, in July the 14th, 2015, so just this past summer, 7,800 miles above the surface of Pluto. This is the spacecraft. Once again, an artist's recreation of the spacecraft, very accurate though. Just to quickly show you the size of the spacecraft, 2.1 meters, so just a little under 7 feet across, about the size of a grand piano. We have a suite of very advanced instruments. The most advanced instruments to fly on a planetary spacecraft up until this point. We had the LORRI instrument, the long-range reconnaissance imager built at APL. Those are our eagle eyes to get the highest resolution images. As we flew by Pluto, we got images that have a resolution about a football field size resolution at Pluto. Okay? If you were flying over New York City at that same distance, you would be able to see the individual lakes in Central Park. And that's the kind of resolution that this instrument provided at Pluto. We had a color camera, infrared spectral imager that allows us to map the composition of all of the objects in the Pluto system. We had an ultraviolet spectrograph that was used to measure Pluto's atmosphere. We had a couple of particle instruments that measured the plasma in the vicinity of Pluto. And then we had, as part of the antenna system and the communication system, a radio experiment that allowed us to probe the temperature and the pressure in Pluto's atmosphere as we flew by, and I'll talk a little bit more about that in a minute. This is just showing you the actual instruments themselves, and I don't want you to have to go. I'm not going to go through each one of these instruments, but the point that I want to make, to you right now is down at the bottom, is summarized down at the bottom. What we needed to enable this mission was to have not only powerful instruments, but they had to be lightweight and very energy efficient. Okay? We could not fly giant solar panels out at Pluto. The sun is 1,000 times fainter at Pluto's distance than it is here at the Earth. So we carried a radioisotope thermoelectric generator to provide the power. So we were a nuclear-powered mission. But still, at the time of the flyby, we only had 200 watts total. All of those instruments together, turn them on all at the same time, they still draw less than 30 watts of power. So for less power than you're required for a light bulb in your house, you could run all of the instruments on the New Horizons mission. And they weighed less than 70 pounds altogether. The weight of all of these instruments was actually less than the single camera on the Cassini mission. Okay? But we needed that because we had to be as lightweight, as energy as possible to be able to even enable this mission to go all the way out to Pluto. Okay, so let me just remind you about the Pluto system. As Frank was saying earlier, Max Muschler and I and other people on the New Horizons team, when the mission was selected back in 2001, we only knew about Pluto and Charon. That was, and the mission was already approved to go to those two objects. But at that point, we realized, well, we're going to go there. We should take inventory of what's really around Pluto. We used the Hubble Space Telescope in 2005 and discovered two new little moons, Nix and Hydra. Hydra here, Nix here. And then a few years later, in 2011, 2012, we found two more little moons, Styx and Kerberos. So we lucked out here. 6 for the price of 2. Okay, this is the deepest picture ever taken of the Pluto system with Hubble. And we could just barely see Styx in this image. Over 100 minutes with this very powerful WIF-3 camera, and we could barely make out Styx. This was a fantastic technical achievement. Okay, but we're actually going to go there, so we can say a lot more. As far as the scientific objectives of the mission, don't worry about reading all of this. The most important scientific objectives of the mission can be summarized by 3 phrases. And those are highlighted at the very top here. Basically, what does Pluto and Charon look like, and all the other objects in the Pluto system look like? Okay. What's the composition of Pluto and Charon's surface? Okay, we want to map the surface composition. And then finally, the third major objective of the mission is to characterize Pluto's atmosphere. So that's what we were after. And these were put together by consensus in the scientific community. Now, we like to call 2015 the year of Pluto. We actually started observing Pluto with New Horizons way back in January. We had approach phase 1, approach phase 2, approach phase 3, and then our departure phases. But really, most of the action, all of the best results come within plus or minus a day of that time of closest approach on July the 14th. That's where most of the action was. That's this purple region here. All of these objectives were accomplished during those couple of days. Okay, now, that's just for background. Now let's just talk about some of the exciting results. Okay, so this is the best that we could do prior to the New Horizons mission. This is a Hubble image taken in 1992. It's a pixelated blob, right? But you can see, this is an amazing technical achievement. You can actually, Pluto's 3 billion miles away. You know, it's only about 1,500 miles across. And from that great distance, you can still make out bright and dark patches on Pluto's surface. But look what happens when you actually go there. This is the iconic view. This is the lesson of 50 years of space exploration. If you really want to make this huge leap in your understanding of a system, of planets, planetary objects, you have to go there. And it turns out, just by coincidence, at the time of the closest approach, July the 14th, 2015, exactly 50 years to the day that Mariner flew by Mars in the very first planetary encounter of an extraterrestrial planet. And that's just a cool fact. Okay, so this is the iconic view we now have of Pluto. You see the so-called heart of Pluto. This region here, which we call Tombaugh Regio, named after the discoverer of Pluto, Clyde Tombaugh, an American astronomer. This is a giant sheet of a very exotic ices, molecular nitrogen, carbon monoxide, and methane. Okay, just a sheet of ice, a giant glacier, basically, 1,000 miles across. Okay, you had this incredibly bright area reflecting about 70 to 80% of the sunlight off of it. And then around the equator, by the way, the pole is here. This is the equator, runs like this. The geometry is very funny. Pluto's tilted over, but the equator is running along this region. Right next to, let me just bring this, by the way, this is natural color. This is our best representation of what we think your eye would see if you were there on the spacecraft flying by Pluto, okay? Just a huge variation in brightness between about 70% reflectivity here down to about 10% down here, okay? And that's because, unlike this region, which is just covered with ice, this is a region that we think is primarily comprised of, complex hydrocarbons, okay? What we call tholins are coating the surface of Pluto in this region. If instead of trying to make Pluto look like what your eye would see, instead of doing that, if you instead take the different color filters and stretch them so that you emphasize the differences, you get a picture like this, in which you now see the heart actually breaks into two ventricles, two very different ventricles. They have different colors, and that's telling you something about the compositional differences that are being displayed across the face of Pluto here. You see this sort of a light brownish mix at the top. You see the very dark reddish region of complex hydrocarbons down here, and this very bright icy region right there. And then you can do things like putting it on the globe and just rotating it around. Now, Pluto takes 6.4 days to rotate completely around, but we're flying by at 30,000 miles an hour. We only get a great view of one side of Pluto, okay? And that's this region here. This, of course, so what we did here was take the globe, and then turn it into a map, just like what you see for the Earth, okay? So the region that we map at high resolution is shown here, and this really doesn't do it justice. Really, I recommend that you all go to our website and download these images, which are available to the public, blow them up, and then roam around, just to be amazed. There's so much detail in these images. But this is the region of Pluto the face of Pluto that we see very well with the New Horizons mission. And we've already started naming informally. These won't be accepted, for a couple of years. It takes a long time to go through the naming process. But as I said before, the heart of Pluto we're calling Tombau Regio, and you can see, we name various other areas after spacecraft, for example, Voyager, Venera, Pioneer, so forth and so on, and then we have craters named after individual people. But you can see the region that the other side of Pluto that we don't see as well as high resolution, but we still see dramatically better than we could from any Earth-based platform. Okay, now, just to orient you a little bit, let's fly over that region of Tombau Regio called Sputnik Planum. Okay? So we're going to fly over that using actual images from the New Horizons spacecraft, starting down here and then working our way around. Okay, this is just look at the landscape. This is as if you're flying. These are actual images, though, taken by the New Horizons spacecraft. We just passed over the mountain range, and now this is a region of what we call chaos region, and then up until the northern edge of Sputnik Planum, and then just swinging back around to give you the view of the whole planet. Okay, now what I'd like to do is once again put up the whole face of Sputnik Planum, and now just highlight about 6 different regions to focus in on. Because like I say, just looking at the whole globe, you can't really appreciate the detail that we're seeing by from the images that we took during the closest approach. So we're going to look at something that we call we have mountain ranges down in this region of Sputnik Planum. We have a couple of isolated mountains down here. This is actually our highest resolution images that you'll see in just a few minutes right there. This is the region where there's chaos. We have glacier flow up here and then what we call snake skin here. So let's just walk through those and show you some of the detail that we get. Okay? So that giant ice sheet is actually moving just like the glaciers do on the Earth. And the evidence for that is these little swirly things. You see where there are barriers, you see what appears to be flow lines of the ice. This is very soft molecular nitrogen ice flowing around barriers as we head into the highlands area above Sputnik Planum. And then you see it reaching the upper highlands area here. And for scale, you can see 20 miles down here. And look at all these weird structures. Okay, this is just another example, except that instead of flowing out of Sputnik Planum into the highlands, we have it flowing the other way. What we think is happening in this case is this pitted terrain over here. We have the ices sublimating from this region, in other words, evaporating from the surface, condensing back into this region, and then finally that ice is now flowing back downhill back into Sputnik Planum. So you have this transport of material from here over to here and then back again, flowing through these channels. Okay, so this is a channel just a couple of miles across. And if you look at it from a completely different kind of angle, that was a high sun where the sun was almost like at noon, as opposed to looking at it at a very large angle. You can see the flow lines even better. Okay, so these are channels that are channeling that ice coming down from a high region down to a lower region. Okay, we have mountain ranges on Pluto's surface. We have the Norgay Montes over here, this mountain range. These are about 11,000 feet high, so approximately the height of the Rocky Mountains in the United States. And then the Hillary Montes over here are about the size of the Appalachians. Okay, you got these are, you know what these are? These are actually giant icebergs sticking out of the crust of Pluto. Water ice. Pluto is so cold, the temperature at the surface is like minus 390 degrees Fahrenheit. approximately, on the surface. So water ice isn't like water ice that you have in your freezer at home. It's like a rock, okay? But that rock is, as you know, water ice becomes less dense when you freeze it. It's actually sticking up out of the crust and floating on this molecular nitrogen ice. Now you go to another region up along the western side of Sputnik Planum, and look at these things. And here's the scale, 50 miles. You've got just a mess of giant boulders. These are icebergs, essentially. Once again, water icebergs, we think, probably being lifted up from the crust. There's upwelling and downwelling, happening in the crust of Pluto, we think. Okay? There are planetary processes, tectonic-like processes taking place that are producing these kinds of things. It turns out that on Europa, one of the Galilean moons of Jupiter, the one that we're planning a mission to now that we think might harbor life, this giant oceans under the surface, also has a region that looks very much like this, although smaller scale. The icebergs aren't as big on Europa as they are here on Pluto's surface. Now look at this. This is just blowing us away. What the heck is this? I mean, we've called this the snakeskin region, these linear features and ponds of ice probably over here. These are ridges. These are called dorsa, but they're almost unlike anything else that we've seen in the solar system. This is Pluto's surface. And then this is one of the highest resolution images that we have down. This is right in the middle of Sputnik Planum in that white area, which is highly reflective, except there are a couple of isolated mountains right in the middle of that, and they're seen here. And just look at the surface, the detail of the surface. I mean, this is an object that's 3 billion miles away that we had only this pixelated view. We basically transformed Pluto from a pixelated blob into this complex, diverse world, right? We've gone from planetary astronomy to planetary geology. The mission has taken us there. Now, just a couple of weeks ago, this is one of the images that came down. I'm sitting at my computer just getting blown away by stuff like this. This is Pluto about 5 minutes after the time of closest approach. So the sun is behind us, okay? The sunlight is coming from directly into the screen here. Look at this. We're seeing not only this incredible surface of Pluto, but a haze. There's a structured haze of particles in Pluto's atmosphere. Okay? This was a surprise to us. But look at this view. And now if you zoom in a little bit, I felt like I was there. Just roaming around. These are, like I say, this is the Norgay Montes, the Norgay Mountains. So these are about the size of the Rocky Mountains. But you see the sun is coming from there. You see the shadows. This is how we tell the size, by the way. We measure the length of the shadows. The sun is coming in, shining in. You see the shadows. We also have stereoscopic views of Pluto. But we're just in the process of getting. We're just getting those down now, and in the process of putting those together. But it's stuff like this, and this is Sputnik Planum once again, viewed from this very low sun angle. It looks very different. Okay, now switch gears, go from Pluto to Charon. Charon is pretty complex as well. This is a flyover movie. Look at Charon. All kinds of stuff on its surface as well. Canyons, deeper and wider and longer, much longer than the Grand Canyon in the United States on Charon's surface. A mountain in a moat. You'll see more about, we'll see that in more detail in a second. And here's our little annotated map of Charon. You can notice the Star Wars themes that we're using here. Vulcan, Planum, Star Trek, I meant. This is a color-enhanced view of Charon. Unbelievable. Look at it. It looks like it's been almost like split across the middle. There's this huge gash in Charon's surface that runs from one end to the other and all the way around. Okay? That's one distinguishing characteristic of Charon, but also the North Polar region has this dark material. It's like a hood of dark material. Where the heck is that coming from? Our best hypothesis for where this is coming from, you notice it's red and dark, just like some of the material on Pluto. We're thinking that maybe some of the material from Pluto's surface actually got transferred over to Charon, and in the coldest regions up in this northern pole, condensed onto the surface and formed this residue. Okay? These are, by the way, I mean, we're just getting these results now. Some of the things that I say may turn out to be wrong. Hopefully not. We've actually had lots of discussions of these things among our team, but we're just in the infancy of analyzing these data. We actually took, in addition to the color image, we took a swath across with our high-resolution camera of the LORI instrument across here, and then draped the colors from the color camera over that, and even higher detail. And here is that's a mountain in a moat right here. So you got a couple of kilometer deep, about a mile deep, moat, and sitting inside that is a giant ice mountain. Okay, the diversity in the Pluto system has just been mind-boggling to us. These are the two largest worlds in that system, Pluto and Charon. They're shown with exactly the same color scheme, okay? So, and they're shown at their observed brightnesses. So this is a true comparison of one object to the other, and look how different they are, okay? So Pluto, has all of this color variation, huge differences in brightness across the surface. Charon is a more muted, grayer object. Okay? But it does have this region. This is why we're thinking that maybe some of this material eventually made it onto Charon. But they're two very different worlds. Just the diversity that we got from the New Horizons mission has been amazing. And like I said, we had no idea what to expect going into this, okay? Because there'd been no reconnaissance of this third zone in the solar system. So this is it. Okay, so in addition, we've actually been able to resolve those small satellites, the newly discovered satellites that we found with Hubble. Instead of little pinpoints of light that you can barely see, we now see them as resolved objects. Of course, they're tiny, so you don't have the kind of resolution that you have on Pluto. But this is Nix, Nix and Hydra, approximately the same size. Okay, these are three different views on approach. Just before approach, and then after we pass by and just look at the little crescent of Nix, well, there's a giant crater in the middle of Nix. And it's colored. It's colored differently than the rest of the object. What does that mean? There must have been an impact occurring, and maybe it excavated down in the interior might be different composition than the surface. I mean, that's our best guess at right now. And look at Hydra. Looks a little bit like Comet Churyumov-Gerasimenko, the rubber ducky comet. You get almost like a double-lobed thing, plus a big chunk taken out here and a chunk taken out here. These things have been battered over the age of the solar system, 4.6 billion years, by meteoritic impacts, and they're rotating, and this thing is rotating really, really fast, probably because it's been impacted. Just quickly, these results are just coming in. Like I said, we had this infrared spectral imager, which is mapping the composition of Pluto and Charon and the small satellites. We only have about half of Pluto's surface mapped right now, but the pink is telling you where there's strong methane ice absorption, and where it's black is where there's hardly any methane. So we get a lot of methane in Sputnik Planum region, but hardly any here. And that's because that methane that was probably there originally has been bombarded by cosmic rays, charged particles, breaking up the bonds, turning it into more complex hydrocarbons that are redder and darker. That's what we think is happening. And now, just to quickly end up with some atmospheric results here, we had a really cool experiment on New Horizons. Shows you this red line here is the trajectory of the spacecraft through the system. So this is the Pluto system. This is what I was telling you earlier about how the system is like tilted over. Pluto's pole is tilted way over, even underneath the ecliptic plane. This is the plane that contains Jupiter and the Earth and the Sun and all the other planets. So we're flying by. The Sun is in this direction, way off to the right. And so this is the shadow cast by Pluto. One of our mission design requirements was to fly the spacecraft right through the center of that shadow, because we had two experiments in mind. Using the ultraviolet spectrograph, as the New Horizons spacecraft went into the shadow, the ultraviolet spectrograph would be looking back at the Sun, and as the spacecraft passed into Pluto's shadow, it'd be looking at the absorption of sunlight in Pluto's upper atmosphere. And by breaking the light up into its ultraviolet wavelengths, you can actually see the signatures of the molecules in Pluto's upper atmosphere. Okay, very characteristic signatures of hydrocarbons, molecular nitrogen, and other species. Okay, that's what we were looking for in the upper atmosphere. But in addition, we had two experiments. The other experiment was to use the radio experiment. We had the deep space antennas on the Earth. These are giant 70-meter antennas. One's in Canberra, one's in Goldstone, California. So over 200 feet across, radiating 80 kilowatts of power up to the spacecraft. Those radio waves are passing through Pluto's lower atmosphere and being bent. The radio waves are actually, they change phase as they pass through the atmosphere, and the amount that they change depends on the pressure and the temperature of the lower atmosphere. Okay? And that was the second experiment. And we used both of those experiments to help us to characterize Pluto's very tenuous atmosphere. The atmosphere on Pluto near the surface is about 100,000 times less dense than what it is here in our room. Okay? So it's a very tenuous atmosphere, but coincidentally, it's also made primarily of molecular nitrogen, just like the molecular nitrogen in our room here is about 72% or so, but on Pluto it's more like 90%. Okay, so this is the kind of signal that you get as we flew the spacecraft. So the ultraviolet spectrograph is looking at the Sun, and it sees a signal up here, and then all of a sudden, as we pass into the shadow, it starts to drop. But you see, there's not a nice clean drop. It's actually bent, and that's because it has an atmosphere. Pluto has an atmosphere. If you compare it to what happened when we flew by Charon, you see how much sharper it is, and that's because Charon doesn't have an atmosphere. Well, we're still looking, but at very, very faint levels. It's at least 3 orders of magnitude, a factor of 1,000 less. Okay, so we passed by Pluto, took all these wonderful pictures, but that wasn't the end of the show. I mean, we kept looking at Pluto as we passed by and looked back at Pluto, just a little crescent of Pluto, as the sun was shining through it, and we were surprised because this is where the sunlight is hitting the surface of Pluto. You see this little crescent here, but you see this light all the way around. And that's because Pluto has this haze. The atmospheric haze, there are particles in Pluto's atmosphere that we're seeing scattering of sunlight from. Okay? So Pluto has weather. There are actually a bunch of different layers in Pluto's atmosphere. And we're in the process of trying to understand what the composition of those particles are, how big they are. Those are things that we're working on now. And we actually could see, those little dark lines here. These are the shadows of sun rays coming through. The sun is shining through the atmosphere, and the places where there's a haze, a fog, you don't, you see, the mountain. The mountains are blocking some of it. Okay. Okay. So, all right. So, that brings me to the end of showing you the results from the Pluto mission. Things couldn't have gone better. For that week surrounding closest approach. It was wonderful. But there was some drama, during this mission. Just 10 days before closest approach, July the 4th, we had a scare. Okay? I was actually sitting in my office at home, working on New Horizons data, and I got a frantic call from the principal investigator, Alan Stern. He was clearly out of breath. He had been running. He said, "We've lost communication with the spacecraft." This is 3 billion miles away, 10 days from closest approach, after 9.5 years. Immediately, we're hoping that something has gone wrong with the ground station. It's not something wrong with the spacecraft, but so he came. I said, okay, I'll be there in 20 minutes. I had to leave my house, we were supposed to go to a barbecue that night. It's 4th of July, but we had to send my wife and not me. But anyway, it turns out that the spacecraft had left its 3-axis normal operation mode and had gone into safe mode. This is what was supposed to have happened. Okay, we were supposed to be in this 3-axis mode, and then on July the 7th, that following Tuesday, we were supposed to transition into this special encounter mode where, damn the torpedoes, if anything went wrong with the spacecraft, it was just going to autonomously try to recover, put itself back on its observing timeline, and just fly through any problems, okay? But we had to get to that point on Tuesday, and this is Saturday, the Saturday before, okay? We had spent 2 years putting together that sequence. It's a 9-day sequence, P minus 7 days to P plus 2 days, filling every second with science observations as much as possible, squeezing as much as we could out. And here we are, just a few days out from entering that core, and we'd stuffed it to the max. I mean, really, we did not want to go in and play with that sequence anymore. We had tested it on the spacecraft. We had already run a rehearsal, okay, and it run perfectly on the spacecraft back in 2013. Okay, so we wanted to recover from this fault before we had to engage this what we call the core load. So here's what happened. We went into the safe mode on July the 4th. We exited the next day. People were working around the clock, and just about just a few hours before we were supposed to engage that core load, we actually did get back to square one. We got back to the baseline. And that was testimony to our, our observing team, our mission operations team, and the head of that is called the MOM, the Mission Operations Manager, Alice Bowman, down here at the bottom. She had a cot, and actually an inflatable mattress that she had in her office that she was just running around the clock, but she knew that there was no way she was going to let this mission fail. And fortunately, within a couple of hours of us engaging the core load, we sent down the first images, and these are the first images. Okay, we knew everything was fine. We executed properly that observation. This is Pluto and Charon, and we were on our way. And then there was not a single thing that went wrong after that. The night of the encounter is when we get our first engineering data telling us how things went. We just get a little bit of data. And the thing that I was listening out for was how the autonomy system, if there were any flags that were set indicating that something had gone wrong. Not a single autonomy flag had been set. Everything just ran cleanly. Also, the control and data handling system engineer said he could tell from the telemetry that all the data had properly been transferred from the instruments to the solid state recorders. So, we knew that the data had been captured. And at that point, we knew that we had a successful mission. And now is really just starting Labor Day weekend, we've started sending back the data. We're so far away, we only have this 2.1 meter antenna. We have this very sophisticated transmitter, but being so far away, we can only send the data back at a maximum rate of 2 kilobits per second, so 2,000 bits per second. So unfortunately, it takes a fairly long time to send these images back. So we're going to be doing this for the next year, but the good part of that is that it's been like going to a toy store. This is a candy shop. Every day, I mean, as we speak now, we have passes every few days, for several hours each day. We're sending down these data. I come into my office, turn on the computer, and look at the images, and it's just, unbelievable. And, people's jaws are dropping to the floor. It's just been amazing. The big surprise of the mission so far has been the complexity and the diversity of the objects in the Pluto system. We had no idea that these dwarf planets, is Pluto a planet or what? The planetary processes that are taking place, we don't have an explanation for why they're happening yet. But that's what we'll be working on. We'll have to try and explain it. Presumably, Pluto isn't alone. There are a handful of other objects that are close to the size of Pluto in the Kuiper Belt, and probably similar processes are taking place there. Let me just mention, this is my last slide. In fact, we're already 7/10 of an AU past Pluto. So the distance from Venus to the Sun is how far we're away from Pluto already. We're still traveling over 30,000 miles per hour. So we're heading deeper into the Kuiper Belt. In fact, we'll be passing through the densest part of the Kuiper Belt in a few years from now. And it turns out we have found an object that we can also fly, that we could fly the spacecraft by. We had to use Hubble. Hubble rescued the extended mission for New Horizons. If NASA approves the extended mission, we had to find a Kuiper Belt object that was nearly along the trajectory of the New Horizons mission, the New Horizons spacecraft. We had a limited amount of fuel to change that trajectory. Okay, we could only change it by plus or minus 1 degree. Okay, so you imagine a cone in space, along the trajectory. We had to find an object that was somewhere in that volume of space, and that was no easy task. We tried for several years with the biggest ground-based telescopes, and were not successful. But Hubble came through last summer. We discovered a handful of objects, including what we call PT1. There were several people in the audience, by the way, who helped work on this. But it turns out that this object, PT1, which is officially known as 2014 MU69, a relatively small object, we think on the order of 30 or 40 kilometers in diameter. But we're going to be doing a burn on the spacecraft, a trajectory maneuver correction, in later this month and in early November that will set us on a path that will send us near that object. And we'll write a proposal to NASA next spring, making the case, the scientific case, for conducting a flyby. And if NASA approves, then that's what we'll be doing on January the 1st, 2019. We already know that's the day of closest approach to that object. But we need the support, of NASA to do that. We'll put in the proposal. Everything is working beautifully, so we hope that they're going to, accept this. And it turns out that object is a Kuiper Belt object also, like Pluto is, but it's in one of those other. There are 3 families of Kuiper Belt objects. It's in one of what we call the cold classical Kuiper Belt objects. Pluto is in a resonance with Neptune. It's a so-called resonant Kuiper Belt object. Could be very different from the cold classicals. The cold classicals, we think, are objects that probably formed in place where they are and have stayed there for their entire 4.6 billion years, relatively undisturbed, and may be more representative of the most pristine material in the outer solar system. So we're looking forward to that. And with that, I'll by the way, please, go to our website, pluto.jhuapl.edu. We have new results coming in every day. Every week we've been having a new release. And so if you want to keep up with what's going on, go there and download some of the images and play around yourselves. Thank you very much.
Thank you, Hal. That is definitely a new look at something that, I will be honest, we thought was going to be relatively boring, okay? Right. I mean, come on. We just thought it would be pockmarked with craters and look like, the moon. Ice craters. But, but look, I thought it would look like some of the Galilean moons, honestly, right? Mm-hmm. I mean, we have all these 4 Galilean moons. We had a bunch of other largish moons. And those were, in my brain, the prototype for, that's what Pluto's going to look like. And, but we'll discover something cute.
In fact, I think the Galilean satellites are actually, they're extremely interesting. But the reason why they show so much diversity is because they're in the deep gravity well of Jupiter, and they have these tidal interactions with Jupiter that can heat their interiors. Pluto doesn't have that. Okay, what the heck is causing all of this activity? What appears to be tectonic activity, upwelling of material, on massive scales. It's a mystery right now.
Well, it's something I'm sure you'll enjoy solving for the next decade or 2 years. All right, I'm sure we have some questions. Over there on the left-hand side. I always
fake the right-hand side, so let's get the left-hand side going today.
I heard you describe two families of KBOs. What's the third family?
Okay, yeah. The third ones are called scattered disk objects. Those are what we think is the source population for the short period comets. They typically have very much more inclined orbits. They've been bounced into those orbits by interactions probably with Neptune as those outer solar system giant planets push their way out, and they ejected some of those, some class of Kuiper Belt objects into those kinds of orbits, and they ultimately are the source region, we think, for the short period comets, like Comet Churyumov-Gerasimenko.
So you think there is some tectonic activity or volcanism maybe going on?
Yeah. I mean, we're actually seeing some streaks on the surface, and there seems to be massive upwelling and downwelling of material. Now, Pluto's gravity is only 1/6 of the Earth, so you don't need as much, something that's a couple of kilometers on Pluto's surface is the equivalent of hundreds of feet on the Earth, in the sense of how much gravitational potential is needed to keep it supported at that distance, But there really is just so much, structure, so many different kinds of terrains, and many of which have some similarities to things that we've seen in other solar system objects, and that's what we do. We try to make comparisons. But the thing that, as I was saying, that's so unique about Pluto is it doesn't have a giant planet next to it that's churning up its interior. I mean, at one point in the distant past, near the time of the formation of the solar system, there probably were radioactive nuclei in the center that caused extra heat, in addition to the gravitational collapse heating the interior. But we think we thought that would have dissipated a long time ago. So what's causing relatively recent activity on Pluto's surface and Charon's surface is the mystery.
And where does the Oort cloud fit
in? Yeah. So the Oort cloud, that was populated by objects that were planetesimals that were in between Jupiter, originally between Jupiter and Neptune, that got ejected, not completely from the solar system, but into this giant, almost spherical cloud that extends nearly to halfway to the nearest star, but it runs from about 10,000, 10,000 AU to 100,000 AU, a giant spherical cloud surrounding the sun. And then also there's something called the inner Oort cloud, which is just beyond 50 AU, beyond Pluto's, the farthest that Pluto goes out. That also, we think, is a source region of the Oort cloud. So that is the biggest single entity.
And is that part of the third?
Yeah, right. I mean, I would really call that the fourth.
So we have a question that's similar to that from our online audience. It says, is it true that New Horizons discovered 2 cryovolcanoes on Pluto?
We have not said that yet, for sure. We see these streaks which are very, we saw these streaks on Triton, Neptune's largest moon. As Voyager flew by, there's these dark streaks that people were assuming were volcanic activity. But even there's controversy about that interpretation. There's so much flow of material on Pluto as we have a chance to digest this and actually look more carefully. Even some of the higher resolution data that will be coming down, we'll be looking for evidence of stuff coming up. I mean, that stuff has to come from somewhere. That molecular nitrogen, was there a giant impact, for example, that hit in Sputnik Planum region, and now you're seeing whatever molecular nitrogen inventory was beneath Pluto's surface has now come up and frozen out there. Those are the kinds of hypotheses that we'll be testing.
Okay, there.
How much of the data has been downloaded so far?
Yeah, so during July we only had 5%, but now it's just coming down, and we have probably by mid to late October we'll have most of that data that's relevant for the group 1 objectives, the 3 most important objectives. Most of that data will be down before we do that burn, which is good.
Okay. In the back, way in the back. Let's go there.
My question is about the nitrogen. I know that you said it's sort of like glacial in a way, but when it's not exposed to the sun,
Yeah.
so to speak, is it cold enough for that nitrogen to sort of be more of a liquid, sort of slushy form? And is that maybe possibly why you're seeing something that...
Well, that would go the other way. I mean, as it gets colder, of course, it becomes more solid-like, and if it becomes warmer, then it becomes more slushy, right? Yeah, yeah. But, you know, there's clear evidence of... This stuff is extremely soft. I mean, it's only, you know, like I say, it's like minus 390 degrees Fahrenheit. And when you look at, I mean, we have you know, in the labs on the Earth, we can actually measure the properties of these kinds of ices, and they are, you know, they're very soft and relatively porous, and they can be moved easily. It's the role of nitrogen on molecular nitrogen on Pluto seems to have the same role that water ice plays on the Earth.
Could you ski on
The
it?
analogy seems to be. And then water on Pluto, on the other hand, acts more like the rocks that we have on the Earth. So, I mean, instead of having a hydrological cycle on Pluto, we have a rheological cycle with nitrogen playing the role of water on the Earth.
Okay, so we had a question similar on that similar thing. Will the ice flows on Pluto change as Pluto heads out to aphelion? Is the temperature difference from 30 AU to 50 AU going to be enough to really change the chemistry of it?
Yeah, I mean, you know, so we have someone on our team investigating exactly this point. And in fact, what has been the history of Pluto since 4.6 billion years, and has tried to trace back to several hundreds of millions of years. You know, what portions of Pluto have seen more sunlight and less sunlight, and exactly what would have happened to the atmosphere. Because as you go farther away, as things cool down, you expect the atmosphere to freeze out. You know, in fact, that's one of the things that we were afraid, you know, that we would miss. You know, because we were afraid that as Pluto was moving farther away, we might not have an atmosphere to look at. But that's been proven to be wrong, and maybe that the atmosphere sticks around for most of its existence. We're not sure yet. In the distant past, I mean, the fact that we have some things that indicate that, I mean, we see almost like sand dune-like features, you know, dune-like features that are sculpted by wind. But you couldn't get that happening with something that's 100,000th, you know, the pressure of the Earth's pressure to, you know, produce that kind of sculpting. So maybe there was a lot higher pressure way back when, hundreds of millions of years ago. These are the kinds of things that, you know, we have to try and explain what we see. We have the data now, we see these things, and somehow we have to come up with explanations.
Okay, down front here.
How long does it take a signal to get from Earth
Yeah.
to spacecraft?
All right, so one way is 4.5 hours. So, you know, you put a flashlight on from Pluto's sun and back at the Earth, it takes 4.5 hours. That's traveling 186,000 miles per second, right? So, you know, it takes about 5 minutes to go from the sun to the Earth.
Ask the question when you get in the morning, and you write the
Yes.
answer by the time you're ready to go home.
And that's the reason why we had to let the spacecraft operate autonomously. We could not joystick it. There was no way. We had to make sure we had the software had the smarts to be able to deal with any bumps, you know, that happened, anomalies during the course of the running of the load.
Okay, here.
Is it true that the Discoverer's ashes were sent along on this trip?
Oh, yeah. Clyde Tombaugh, his family is just wonderful, by the way, and they came, his daughter and her husband and his son. They actually came to APL for the encounter, and they're really wonderful people. But Alan Stern, you know, he had heard that, you know, Clyde Tombaugh would love to, you know, have flown by Pluto or to see a spacecraft flying by Pluto. So he asked the family, did they want to send ashes? And they sent some of his ashes to APL. We put them in a little container, you know, bolted it to the side of the spacecraft. So Clyde got to fly by. Got to see it.
Right here.
I have two questions. The first one is, did you actually explain to us some weather that you observed where materials were sublimating from one area and then floating through the atmosphere?
Well, you know, we see the sort of the ice flowing in two different directions, you know, in different places on Sputnik Planet. But that one part that looks like pitted regions, it looks like, you know, there was ice originally there that came back down into Sputnik Planet, but didn't how did it get there in the first place? We think that it sublimated from Sputnik Planum onto that region and then made its way back. So that's almost like a circulation occurring there. But we see these different bands in the hazes. When you look carefully at those hazes, you see different bands in there. And we think that there might be these little complex hydrocarbon particles in Pluto's atmosphere that are causing this haze, that is the haze. I mean, we don't have definitive proof of that yet. In fact, there'll be something coming out this week about that. So.
The other question I have is, do you have any kind of estimate as to how many objects the size of Pluto and with facets like you just described might be in the Kuiper Belt?
Yeah, so there have been already some pretty exhaustive surveys of looking for objects that are around Pluto's size, and I don't think we're going to find too many more that are as the size of Pluto. There are a handful now.
There's a lot of stuff in the Kuiper
Belt. Yeah, there's a lot of stuff, but it follows a parallel. There's many more small objects than there are large objects, and we have a handful of objects that we found that are approximately the size of Pluto within the factor of 2. A couple dozen maybe, but there's been enough searching that I don't think we may find 1 or 2 more, but I don't think there could be many more.
And we should note that the measurements of New Horizons confirmed that Pluto is actually the largest in the Kuiper Belt.
Right. That was one thing.
We had Eris as slightly larger.
Right. Pluto is the king of the Kuiper Belt.
Of course, that's changed by the encounter with Eris, right? I'm sure we're closing to that.
Yeah.
All right here, yeah.
Any chance that your data will bring Pluto back to planetary status?
To a lot of us, we see all these planetary processes taking place that we didn't know existed before, so I think that makes a good case. But almost all of us, have acclimated ourselves to the choice of dwarf planet for objects like Pluto, and I'm fine with that. I mean, the big issue was, is the dwarf planet also a planet? Well, if it has planet in the word, I mean, it's in the name, it seems kind of stupid not to say that it's a planet, but. We don't really, I personally don't care so much about that. It is what it is, and it's a fascinating object, and just the comparative planetology that we like to do by having Pluto and comparing it to Ceres, which you'll be hearing about in a couple of months, and other dwarf planets, and then other large satellites and things like that. That's where the fun is.
I mean, we have in the new solar system, since we've been on Voyager and all these space missions, an amazing number of worlds in the solar system. And the comparison of them, we're comparing moons to planets and planets to dwarf planets and such. It's really that there is just such a diversity in the solar system that we had no idea when we were in school.
Right.
Way back when.
It's revolutionized our view of the solar system. It really has, yeah.
All right, Herman, way in the back.
Thanks.
Herman.
Hi.
Hello there.
Hey, how do you account for the number of craters that you see on Pluto and Charon?
Yeah, well, if you notice, there's a huge difference in the number of craters on Pluto's surface. Sputnik Planum is almost crater-free. We see nothing there. That's why we say that region is probably geologically young. Okay. I mean, Pluto is sitting in the Kuiper Belt. There's a bunch of stuff flying around, especially meteoritic material that's boulder size. If they were they'll be pummeling all of the objects in the Pluto system. If you think about it, over 4.6 billion years, that's a long time. The surface would just be pockmarked with all that. But that's not what we see on Pluto's surface. You see some places on Pluto, like in those very dark regions, Cthulhu Regio, that has a lot more craters. But in the Sputnik Planum, we haven't been able to find a single crater. On Charon, there's a lot of diversity over its surface as well. There's some highly cratered areas, but some regions that are not cratered. So that's why we think there's in fact a diversity in age of the surfaces. And you're judging the age by how quickly it's turned over, and you've erased the cratering record.
Okay, so we have questions similar to that from online. We see evidence of the supposed collision that formed the Pluto system.
That's an interesting question. Yeah.
And just for the audience, I mean, the idea that Pluto can't capture these moons with its gravity. So we presume that there was some sort of collision that pulled the system together.
That's the conventional wisdom right now for how Pluto's system formed was two roughly Pluto-sized objects crashed into each other, this giant collision, and then from the debris that formed in the aftermath, you got Pluto, Charon, and then these, a disk of material that ultimately, within that disk of material, you formed the smaller satellites, okay? And then they evolved outward into their current configurations. That's, as Frank's, and if you noticed, all of the small satellites, and they're all in the same plane. So that kind of screams out at you for this collisional origin as opposed to just capturing from the Kuiper Belt. It's almost impossible to capture it into that kind of configuration. So that's why we favor the collisional origin for the Pluto system. But it turns out when you look at the details, we have not yet been able to explain how to go from that collision to exactly the configuration that we have today. There's some things that just don't quite fit that scenario. So we still have some work there, but I'm pretty sure that it was a giant collision. In the case of Charon, in the case of Pluto, the giant place where we had that giant ice sheet, Sputnik Planum, I'm wondering if that's, a lot of us have been wondering if that's a giant crater, that formed, that filled in with material that came out of the interior and then formed the ice, but when that happened and whether or not that's the explanation, we still don't know.
Okay, over here.
How much longer will the craft be able to operate?
Yeah, so for sure, January the 1st, 2019, we'll be ready to do the flyby of this Kuiper Belt object, this new Kuiper Belt object that's been discovered, if we get approved from NASA. But we could go another 10 years. We have enough power from the radioisotope thermoelectric generators and to do some further observations.
Will that still be in the Kuiper Belt, or will it?
Yeah.
It will.
Yeah. We have already have to pass 50.
And another question about the future. When will New Horizons become the furthest human-made object, surpass the Voyagers?
It never will. Not maybe an infinite amount of time, but those Voyagers, they got nice gravity assists from.
It doesn't
matter.
Like the New Horizons is moving faster.
No, it was the fastest to leave the Earth, but they get accelerated by their interactions with the giant planets. So New Horizons will not catch them.
Ah, okay.
All right, where else? Who was nice? In black in the back. I saw your hand a while ago.
For how long will the science team and research team be funded, and what are the critical decisions?
Yeah, so in fact, that's one of the big decisions about the extended mission. Like I say, we have to write the proposal and make the case, make the scientific case, because there are lots of other, there's lots of competition in the space business for other missions. And it's a matter of, I'm pretty sure that there's a slam dunk that will be approved to do a flyby, but how much money we'll get to support the operations and the science analysis is the issue that will have to be decided by this review. And right now, NASA will be putting out a call to the community, because this is not just New Horizons team's data. We're going to put it in an archive for everyone in the community to be able to use after we get down. We wait about another 6 months after that, we calibrate it and put it up in the planetary data system. So NASA will put out a call for people to analyze those data, and it's only several, it's typically like the whole program, all the analysis over several years might be $10 million or something like that. We don't go into our business to make money.
And now there's water on Mars, right?
Yeah.
Any question down here?
Could you compare the size and gravity of Pluto to our moon?
Yeah. Okay, so Pluto is about 3/4 the diameter of our moon. So our moon is bigger, and that's one of the reasons why people didn't, wanted to demote Pluto. In terms of the moon is much more massive because Pluto's density is only about 2. The moon has a density of about 5 or something.
Imagine 1/6 gravity.
1/6 the gravity of the surface of Pluto compared to the surface of the Earth.
So you said something that would jump off there would go how many?
Yeah, so that's why you can build up, ice mountains higher. There it's easier to build up things because the forces on it are that much weaker, and so you don't need something It's just like on a comet nucleus. You can have spires that are hundreds of meters high. Even though it's a very fluffy, porous material, because there's hardly any weight associated with them.
Jumped on.
Yeah, if you jump. Escape velocity is on the I don't know.
You might not come back down.
That's what we're worried about.
You jump pretty high.
We went upstairs and all shuffling around on the moon, and that wasn't 1/6 gravity. There was something wrong with that picture.
If you want to please
Anyone
don't
can
want
jump
to.
on Pluto.
Yeah.
Let's get off that subject.
All right, it's about 9:30. One more question because we have to cut it off and let people go home.
Maybe a speculation, but the Oort cloud, Kuiper Belt, the Oort cloud, is that generic enough that you might assume that other solar systems spread around would have similar?
Oh, absolutely. I mean, this is one of the reasons why this is important, is to figure out, well, what is the exact architecture of our solar system? And while we should be unique, and there's billions of stars out there, there must be other systems that are like this. In fact, we already have direct evidence of disk around other stars that are similar in nature to the Kuiper Belt, and we also think that there are probably Oort clouds around some of those objects.
Elliptic disk on other stars.
Yeah.
And then a spherical shell.
Yeah. See, those kinds of things.
All right, ladies and gentlemen, you now know almost everything there is to know about Pluto. But there will be more cool stuff coming down every week. You're doing Thursday press releases, right? So go to this website every Thursday. You'll get your weekly dose of new cool Pluto coolness. And when we say coolness, we're minus 360 degrees Fahrenheit coolness. So ladies and gentlemen, one more big hand for Alex. Thank you for coming. We'll see you next month.
Oh, thank you.
I'm how enthusiastic. I mean, it's exciting.
I know it is. It's hard for me.